Hey everyone, and welcome to today's Explainer. I am, absolutely thrilled you're here with us today because we are tackling a truly massive topic. We're going to explore exactly how modern science is gearing up to solve what's basically one of its greatest boss battles. And they're doing it using this incredibly evolved tech stack. So get ready, because we are merging high-performance computing, artificial intelligence, and quantum mechanics. The whole shebang.
So, can a computer predict chaos? I mean, it kind of sounds like an oxymoron, doesn't it? But this right here is the ultimate challenge of predicting complex real-world systems. It's basically the Everest that computational scientists have been trying to summit for decades. But before we start building out our technological solution, let's make sure we really understand the challenge itself. When we say chaos or complex systems, we aren't just talking about a messy room. We are talking about tangible, physical realities. Things like weather patterns, the fluid dynamics of ocean currents, or the unimaginably intricate dance of molecular interactions. In these systems, you have these highly nonlinear, multidimensional interactions. That means a tiny change right now can result in a massively different outcome down the line, and that makes long-term prediction exceptionally difficult.
And these abstract, chaotic datasets, they actually map directly onto our very human environments. Take a look at this simulation of a city's complex telecommunications infrastructure. A failure in just one single node can ripple chaotically through the entire grid in ways that are incredibly hard to foresee.
And zooming in even further, from broad infrastructure down to a highly granular level, we can even track individual vehicles and pedestrians. Predicting these complex systems isn't just some abstract academic exercise. The stakes here involve everything from accurate climate modeling to emergency response and even advanced urban planning. All right, here's our roadmap for today's Explainer. First, the problem with chaos. Then, pushing supercomputing to limits. AI meets Earth systems, the quantum computing leap. Quantum AI tames chaos. And finally, a heterogeneous computational future.
Let's jump into Part 1, Pushing Supercomputing to Limits.
For decades now, the absolute heavy lifters of the scientific world have been high-performance supercomputers. And I want you to just take a second to let this staggering number sink in. 1 quadrillion. That is the number of degrees of freedom, which is basically the number of independent moving variables recently calculated by the exascale supercomputer El Capitan in a single computational fluid dynamics problem. 1 quadrillion. It is literally the largest fluid dynamics simulation ever performed, a total marvel of brute force calculation. But here's the catch. Even with numbers this massive, brute force just isn't enough anymore. Because despite these immense capabilities, we are slamming into fundamental physical and thermal walls with traditional computing. Moore's law, the famous prediction that transistor counts double every 2 years, well, that's noticeably decelerating. Dennard scaling, which allowed chips to run faster without needing more power, that actually died back around 2006. Today, we're severely bottlenecked by just trying to move data around. And the sheer power and liquid cooling constraints of these massive machines, they're becoming completely unsustainable. We are practically having to build dedicated power plants just to keep the computers cool. We need a shortcut.
Which brings us to Part 2, AI meets Earth systems. So, could artificial intelligence be that shortcut? Could it bypass our computing limits? Well, we face a pretty massive trade-off here. Traditional physics-based modeling is incredibly high fidelity, sure, but it is agonizingly slow. On the other hand, machine learning models, like the hybrid neural GCM used for Earth system modeling, are lightning fast and cost way less to run. But there is a catch. Over long periods, AI is prone to something called drift. It loses spatial stability and errors just rapidly accumulate. It's kind of like trying to draw a map from memory while wearing a blindfold. Eventually, the AI simply loses track of the actual real-world physics.
Moving right along to Part 3, the quantum computing leap. To fix that drifting AI, we need a technology that processes data fundamentally differently. Enter quantum computing. Looking at this projected scalability curve, you can see this isn't just theoretical math on a chalkboard anymore. It maps a very real hardware trajectory. We are steadily moving from small, noisy systems towards highly capable, fully error-corrected quantum machines.
Let's break that timeline down really quick. In 2023, we were in what's known as the NISQ era, Noisy Intermediate Scale Quantum. These machines are powerful, yeah, but pretty error-prone. But look ahead toward 2050, and we expect early fault-tolerant systems, which will eventually lead us to full-fledged fault-tolerant quantum computers by 2080. The quantum hardware is steadily evolving to actually correct its own physical noise, which makes it an increasingly reliable tool for deep science.
And that leads to part 4, the really exciting stuff. Quantum AI tames chaos.
This is literally the climax of our explainer today. What actually happens when we take that lightning-fast AI and patch its drifting problem using quantum computing? Well, researchers at University College London had this massive aha moment. They didn't try to run the entire simulation on a quantum computer. That would be way too much. Instead, they built a hybrid system. They used a low-temperature 20-qubit quantum computer purely as an offline preprocessor for an AI model.
This hybrid workflow breaks down into 3 beautifully elegant steps. First up, feature extraction. The quantum computer processes the raw simulation data. Because it uses quantum entanglement, where particles are fundamentally linked and share information instantly, it can easily capture highly nonlinear, hidden correlations that classical computers completely miss. Second is pattern isolation. It identifies statistical properties that remain stable over time, even amidst all that chaos. And third, classical AI training. Those stable, quantum-derived patterns are fed into a classical supercomputer to guide and train the AI.
And what was the result of all this? A massive 20% improvement in prediction accuracy over purely classical AI models. 20%. By giving the AI this quantum-derived anchor, it just stopped drifting. It stayed completely stable over extended periods, even when modeling deeply, deeply chaotic systems.
But wait, it gets better. It wasn't just more accurate. By compressing those high-dimensional chaotic states into stable, invariant representations, the system required hundreds of times less memory to maintain its stability. Think about the real-world stakes here for a second. We can now predict the chaos of fluid mechanics and atmospheric dynamics using vastly fewer resources. This completely opens the door to incredibly accurate real-time climate forecasting, precise cardiovascular modeling, and maybe even controlling viable fusion reactors. It's a total game changer.
Finally, our last section, a heterogeneous computational future. Pulling back for a minute to look at the big picture, all of this builds into what we're calling the post-Moore era ecosystem. You see, the future isn't about quantum computers just swooping in and replacing supercomputers entirely. Not at all. It's about a heterogeneous environment. We're going to see unified software stacks that let us work seamlessly across all different types of hardware. We'll rely on AI-augmented models, serial loops seamlessly passing data back and forth between quantum and classical processors, and a major focus on balancing the trade-offs between time, energy consumption, and high fidelity.
This whole paradigm shift is captured so perfectly in a quote by Professor Martin Schultz from the ISC High Performance Conference. He said, "The next era of scientific capability will be measured less by peak floating point rates and more by time-energy fidelity trade-offs across end-to-end pipelines. We are officially moving away from obsessing over raw, brute power and moving towards smart, integrated, and highly efficient problem-solving."
Which leaves us with this final, really thrilling thought. We've proven that by combining these technologies, we can actually tame the chaos that has baffled scientists for generations. So, if quantum AI can predict the deepest chaos of our physical world, what previously invisible facets of reality will it allow us to uncover next? Thank you so much for joining me on today's Explainer. Keep learning, keep questioning, and I'll catch you next time.